Okay, so let's get started. We've discussed Python lists and tuples before, but let me review a little bit and then go on to discuss Numpy arrays and Numpy linear spaces. These are the ones that are typically used. These are the constructions that are typically used when doing numerical computing. So once again, if you want to construct a list, one way to do it is to put the elements of the list between square brackets, right? And you've created a Python list. Okay, one thing to remember, Python starts counting from 0. So my list of 0 gives you the 0th element in the list, which is in this case 3. My list of 2 would give you the last element in the list, right? So this is element 0, element 1, element 2 is 2. And remember that if you put in -1 in the index, if you put in an index of -1, that means the last element in the list, which in our case would again be 2. So that's useful if maybe you have a whole bunch of lists and you can't remember, or you don't want to remember how many elements there are in each list. Then whenever you need the first one, you can always get it with 0. And whenever you need the last element of the list, you can always get it with -1. Okay. Changing, so tuples, you can't change tuples once you've constructed them. With lists, you can. So if you want to change the last element of the list, in our case, that's 2. If you want to change it to the string haha, then you can say my list of -1. The last element of my list should now be set to be equal to the string haha. And now if we print the list, we see that the change has occurred. If you try to do this with a tuple, that wouldn't work because you're not allowed to change them. Okay. Now, a few other things that you can do with lists that might be useful. So for example, if you're running a program in a loop and you're constructing the value of some function at different times, then you might want to start with an empty loop, and then you might want to append an element to your empty list as you go along. Okay, so we have the capacity to append things, and so we have the list. In this case, we were calling it my list. We already had it. Dot append. So now you have the list that you already have, and I want to extend that list by one more element. I want the last element to be the string boo-hoo-hoo, right? So I say append, and then in round brackets, whatever you want to append as the last element of your updated list, you do it this way. And now if we print my list, we can see that this new string has been added to the end of the list, and the list is now longer. Okay. In some cases, we want to delete elements of the list, either from the front or the beginning or somewhere in between. So yeah, I don't have time to go through all the things that you can do with lists, but one thing that's quite often useful is you want to pick out the last element of the list. Now the list shrinks. That last element is no longer part of the list, and you want to return it. So if I say x equals my list dot pop, and then there's nothing in the round brackets, what that means is set x equal to that last element and remove that last element from the list. So the length of the list shrinks by 1. Okay. So now if I ask you to print x, it prints what used to be the last element, the string boo-hoo-hoo. And if I print my list, we see that it's shrunk. boohoo is no longer part of the list. Okay. Now, slices of lists. Okay, so let's create a new list. So here's a list of sciences. Okay, Sci is the list: biochem, geomath, and physics. So I've just created a list of sciences. Okay. Now I ask for a slice, Sci 2 to 4. Okay, you may recall that what that meant was I want a sub list, a slice of the list consisting of the elements of Sci starting from Sci of 2 to 4, but it doesn't include 4. So this is Sci of 2, Sci of 3, and not Sci of 4. Okay, so Sci of 2 is what? 0, 1, 2, it's geo. Sci of 3 is math, and Sci of 4 is physics, but that doesn't get included. So this should return geo and math, which it does. Okay, there are probably good computer sciencey reasons why we don't want to, why we do it this way. Okay, but okay. Now, if I want to take a slice to the end, just don't specify. Okay, if you knew the end, right? And if we knew that there were m elements, and I said Sci of m, but maybe we don't remember. I don't remember how long Sci was, but I want a list which goes from element with index 3 to the last element, including the last element. Then I can just write Sci of 3 colon. Okay, Sci of 3, 0, 1, 2, 3. So starting from math and going until the end, which is physics. So I get math and physics. Okay. And if I want to start from the beginning, so Sci of, and in the index here, for the index, you write colon 2. That means start from the beginning and go all the way up to 2. And remember, when we write a number in, that's exclusive. It doesn't go all the way up to 2. So this would be the beginning is 0, 1, and 2 doesn't get included. So this should give me back bio and chem, which it does. Okay, and if we want the entire list, we just write a colon, Sci of colon, and that will give me the entire list. Okay, if I wanted the entire list excluding the last element, then remember -1 means last. So if I put that in, that means up to the last element, but not including the last element. Okay. Now, if I have a slice and then I set that slice equal to something, then that changes the original list. Okay. So if I say Sci of 2 to 4, that means Sci of 2, Sci of 3, not including Sci of 4. And then I say, so Sci of 2 and Sci of 3. And, well, I set those equal to astro and econ. Okay. Now if I print Sci, then 0, 1, 2, and 3, Sci of 2 and Sci of 3 have been replaced by astro and econ. So if I say that this slice is equal to something, then I've changed the original list also. Okay. All right. One thing that you can do is you can loop over a list. So I can say for x in Sci, right? So one thing to do was you could have an index. You could say for I and give it, the range that I takes, and then say Sci of I. But you actually don't need to do that. you can say X stands for elements in Sci. I'm going to go through them, through the list in order, starting from the first one to the last one. So for X in Sci, print X, and it will go through each X is set to that part in Sci, and then it will print each one. Okay. Okay. Now, sometimes it's this is a small example, so it's a little bit silly, but sometimes there are good reasons for creating an empty list first and then filling it as you go along. So here's an example. I'll let squares be an empty list. To make an empty list, just put square brackets, and then we can loop over X inside, let's say, and for squares, I want you to append the string to this list squares, and what it is this element in Sci, and then we put them together, so that means it's concatenated. Since the X are all strings, they're concatenated. That's what the plus means, right? And then put that in as an element of the list squares. So you get this as the result as shown. Okay, so that was just a brief review of lists. For numerical programming, typically what we want to use are, there's a module called Numpy, and Numpy has something that are called arrays. So those are arrays of numbers which with some numerical capabilities associated with them. Okay, so we would typically want to use Numpy arrays rather than lists of real numbers. I would rather have a Numpy array of real numbers. Okay, so Numpy arrays. All right, so it's a type of an array that we can do numerically useful things with. They're defined in a module called Numpy. Okay, and so let's say let's do a first example of a Numpy array. And what I want to do is, first of all, I want to import this module Numpy. So if I just said import Numpy, then when I was referring to things that are defined in Numpy, I might have to say Numpy dot, and then whatever that thing is. So for example, the value of pi is defined in Numpy, or the sine function is defined in Numpy, or the cos function is defined in Numpy. So I'd had to write Numpy dot cos, Numpy dot sine, Numpy dot pi. If instead I say this, import Numpy as NP, what that means is I want you to import the module Numpy, and when I refer to Numpy, I'm just going to use the shorthand NP. So a lot of people tend to do that. Okay, so now Numpy contains something which allows me to construct an array. Okay, so if this is just written in what's in the square brackets, that by itself would just be a Python list. But I'm saying this says, take this thing that would be a Python list and turn it into a Numpy array. Okay, so that's one way of creating a Numpy array, is just make the, list the elements that should go into your array. Okay, and this might be a way, for example, for you to represent vectors. If you were doing linear algebra, this might be a useful way of representing a vector. So X equals Numpy array, and then in square brackets, a list of real numbers. And now this is a Numpy array containing those real numbers. Okay. Now, let's say you wanted, so we call this a rank 1 Numpy array. If you wanted a rank 2 Numpy array, you might think of 0, 2, 4 as one row of a matrix. And you might think of 6, 8, 10 as another row of a matrix. So you'd say, write the first row as a list, write the second row as a list. Now contain both those rows within square brackets and feed that into the array constructor of NumPy. So y equals np dot array of within square brackets for a list for the first row, square brackets for the second row. And then if I ask it to print y, it gives me something that looks something like a matrix. And so if I want to do a matrix vector type of operation, then x might be the vector and y might be the matrix. Okay. Now, once you've constructed your arrays, you might want to check shapes. Sometimes you are doing operations and they're wrong because the shapes of the associated arrays are wrong. You want to check the shapes of the arrays to make sure that everything's okay. So every NumPy array has something called a shape associated with it. So x dot shape is the shape of x and y dot shape is the shape of y. And if I ask it to print for this x that we created, x dot shape, and if I ask it to print what we created, this y, what is the shape of that array y? It says, well, this x has a shape of, it's a rank 1 with 5 elements, and the other one is, well, you could think of it as a matrix. It has 2 rows and 3 columns. Would be one way of interpreting that. Okay. Indexing is a lot like the indexing of NumPy arrays is a lot like the indexing we had for lists. Remember, you're starting at 0, and so but it's extended into more dimensions possibly. So y of 1, 2 would be, if we go back to y, this is 0 and this is 1. Okay.
I want to ask a question.
Yes.
So in previous, you said that it is specified that it row and columns 2 and 3.
Yeah.
So would it be convenient to that in the space you have print x, you to also mention the rows and column of a matrix?
Yeah, I mean, maybe it should, but it doesn't. So this is basically saying that there's just a row with 5 elements and there are no, don't think of it as having any columns. Okay. All right, so if I refer to y12, this is row 0 and this is row 1, and this is column 0, column 1, and column 2. So y12 should refer to 10, which is what it does. Okay. Okay. Now, if I want to, I can change things. Something like what we did with slices. I had an old x of 0. X of 0 was 0, but now I'll say x of 0 is 5, and now if I print x, all of x has changed. Okay. Sometimes particular types of arrays are useful. I might want to have an array of zeros, an array of all ones. I might want to have an array that I'm going to use as if it was the identity matrix. So or I might want to have an array of all constants. So we consider how to do this. So an array of zeros, the way you do it is you say, all right, let's say I want 3 rows, 5 columns, all of zeros. So A is equal to, and then within NumPy, there's this thing which creates arrays which are all zeros, called zeros. And then I give it the dimensions of that array, let's say 3 by 5. So it gives me three rows, 5 columns, all of zeros. Similarly, if I wanted them all to be ones, then A equals NP dot ones. 3 by 5 means 3 rows and 5 columns, and they're all ones. Okay. And if I want a constant array, is I want an array of all twos instead of all ones, for example, then we use full. So NP dot full here in brackets 3 comma 5 means 3 rows, 5 columns, and then comma whatever you want that constant value to be of every element, in this case twos. So it's a 3 by 5 array, all of twos. Okay, if we want the identity matrix, then that's constructed by something called I. I is spelled IYE. Okay, so NP.I of 3 means the 3 by 3 identity matrix. Okay. All right. Once again, array indexing is like it is for lists, but for each dimension. So let's say I construct this array. A is equal to NP array. First row is 1, 2, 3. Next row is 4, 5, 6. Next row is 7, 8, 9. Okay, so it's a 3 by 3. And now if I start taking slices, let's say I say A, and then for the first part, I put :2. So what does that mean? It means row 0 and row 1 and not row 2, right? It's exclusive. And then for the second part here, I put 1:3. It means start at column 1, column 2, and not column 3. So column 0, column 1, and column 2. Okay, so these two columns and these two rows, what's that slice of the array? It's the part here, 2, 3, 5, 6. Is there a question? Okay. Once again, if
I did not get how we get 2, 3, 5, 6.
Okay. Okay. So let's over here where we're defining B. I'm saying for the row part. Okay. So the first part refers to rows. The next part refers to columns. So the row part says, if you write colon with nothing in front of the colon, it means start from the beginning, right? So starting from the beginning means 0, 1, and here we've written 2. So, but it's exclusive, so we don't go as far as 2. So it means row 0 and row 1. So where's row 0 and row 1? Is that okay?
Yes, sir.
Okay, so that's row 0 and row 1. Now, here it says start from column 1, column 2, but not as far as column 3. Okay, well, what are column 1 and column 2? This is column 1. Sorry, this is column 1 here, starting from here. Oh, okay. This is column 1 and this is column 2. So is it okay now?
Yes, sir.
Okay.
Indexing.
Yeah. Okay. So now B refers to this block over here, 2, 3, 5, 6. Now, if I change B, I'm not referring to A anymore. But Python is remembering that I was talking about A. B is a particular part of A. So now if I change a part of B, B of 0, 0 is here. It's the first element. This is 2, right? Row 0, column 0. That's this element 2 here. Now, if I say make that 100, right? Then this is what it was referring to in A. So that part of A should change to 100. So if I print it, it does. Okay. Is that okay so far?
Professor, so if you could just scroll up a little bit.
Yeah.
So when we're defining B to be a part of A,
Yeah.
any changes we do in B would be sort of go back to A. So it's
Yeah.
referring,
A will change. A will change. You changed B,
okay.
and B was a part of A, so A changed.
Is there a way to sort of extract a part of A to be a new variable?
Yeah, you can make a copy,
Okay.
right?
Okay, yeah, that makes sense. Okay, thank you, Professor.
Okay. Array arithmetic. Okay. So, like I said, these are more than lists. These are things which have been souped up. Okay, so they're more than lists of real numbers. They've been souped up in a way that they have useful numerical things associated with them. Okay, so let's say I create an array. So NP array, the first row is 2, 4, the next row is 6, 8. And let me specify, so this is something I can do. I can specify that the elements that I'm talking about in this array, everything is a 64-bit real number, float 64, okay? If I wanted to be perverse, I could have said it was a float 32, for example. Okay? And I'm going to make y of the same type, and its rows are 1, 1, and 1, 2. Okay? So this is what we've done before. So we've created two 2x2 arrays. Now, what I can say is, I would like you to add these two arrays. So I think, you know, if I wanted to numerically implement some matrix addition, I wanted to add two matrices of the same type, then what does matrix addition mean? It means, you know, Bij add, you know, Aij added to Bij is in the new matrix, right? So it's element wise. So if I say Z is equal to X plus Y, what it's done is it's added 2 plus 1 and made 3, 4 plus 1 and made 5, 6 plus 1 and made 7, 8 plus 2 and made 10. So that's a new matrix created by element-wise array addition. Okay, just like for matrices that you're used to from your linear algebra course. Okay. Another way of doing it would be to use the add function, which lives in NumPy. So NP is our alias for NumPy. So np.add, I'm using the addition method. And what two things am I adding together? I'm adding the arrays X and Y. And we check, and it's the same thing. So these are the two methods, or the two notations, I should say. It's probably the same thing underneath. These are the two notations for addition of two arrays of the same ranks. Okay, two arrays of the same dimensions. Okay, similarly, you can add, and so you can subtract. So Z equals X minus Y, right? The subtraction is done just as is done in linear algebra. It's done element-wise. And the other notation for doing the same thing would be to say Z is equal to I'm going to use the subtract method that lives inside of NumPy. And what two things I'm going to subtract? I'm going to subtract, I'm going to take X and I want to subtract Y from it. So put those two in as arguments and it will give you the same thing. Okay. Okay, multiplication, we need to be a little bit careful. In some circumstances, if I have two arrays of the same dimensions, of the same rank, then I want to multiply them element-wise, right? So if I by C is equal to A times B, what I mean is a new matrix C, which has the same dimensions as A and same dimension as B, and the element Cij is equal to Aij times Bij. Okay. And sometimes by multiplication, what I might mean is the multiplication that we defined in linear algebra of two matrices. And then those are not always of the same dimension, right? Okay. So for the element-wise multiplication, one notation is Z equals X star Y. And this is the element-wise multiplication that I just talked about. And the other way to do it is to say, well, I'm using the multiply method of NumPy, and the two things which are being multiplied element-wise together are these arrays X and Y, and it will give you exactly the same result. Okay. Now, element-wise division. So C equals A times B, or sorry, C equals A divided by B means Cij is equal to Aij divided by Bij. In our case, if we're using these rank 2 matrices. So we write it just as if we were writing an ordinary division. Z is equal to X divided by Y. Okay. And that's also the same thing is done by calling the divide method, which lives in NumPy. X is being divided by Y. Okay. And sometimes this comes up before we get to the proper matrix multiplication. Element-wise square root, you do npi dot square root of X, and it takes the square root of each element-wise. Okay, one by one. Okay, what do you think would happen if I wrote np dot sine of X? What would that give me? Yeah?
Would it generate a similarly ranked matrix with sin x and then give you the dot product of that?
Well, yeah. So if you wrote np dot sine of X, it would give you it would give you a 2 by 2 matrix, element-wise, the sign of each entry. There used to be an X. Okay. So the nice thing about if I wanted to do this with ordinary Python lists, I would probably have to write a loop, right? And go through each element of the array and take its sign or its square root or whatever. But with these methods, which are defined in NumPy, I can sort of say, all right, do this operation to every element which is in the array, without having to write a loop. Okay. Okay. Now, what if I actually want to do matrix multiplication? You know, the proper matrix multiplication that was defined in your linear algebra course. Okay, so you do that with dot. The method is called dot. So to write X times Y, meaning matrix multiplication, it's X dot with Y. Okay. And the other possibility is to write np dot X comma Y, means multiply X by Y. Remember, matrix multiplication, it matters what order you put things in, right? So Okay. Sometimes we want the sum of all elements, right? So np.sum of x means take all the entries which are in the array x, add them up together, and in this case it's 20. Okay. We can, if we want, we can also ask for sums according to the dimension, just in that dimension. So if I want the sum of the column, of all the entries in a column, I'll set the axis equal to 0. If I want the sum in each row, I'll set the axis equal to 1. Okay. And if I want transpose, so if I want the transpose of x, I would say x dot capital T. That would yield the matrix, which is the, if I'm thinking of x as a matrix, then x dot T would give me an array, which I can think of as the transpose of the matrix x. Okay. All right. So, and there's a lot more in there, but maybe that's the minimal amount that we need that we can sort of get started. Is that okay?
Does transpose function also exist in NP?
Yeah, this transpose function is in NP, I guess. So, yeah. Maybe this is an attribute which is associated to. Yeah, I don't know if there's an alternate way of writing that. Yeah. Is there another question?
So I wanted to add on to that. I think it's the one that comes with the base package of Python, because you're not calling that np.t. So it's not the one from NumPy. I'm not sure by the way.
Okay. All right. Okay. Another thing that's useful is the idea of a Linspaces stand for linear spaces. So basically, you're thinking of things as vectors if you want, or you can think of them as vectors. And use linspace when we want arrays of evenly spaced numbers. So here's an example. You'll see what I mean. If I say np.linspace 1, 3, it means give me an array, and a NumPy array of numbers that are going from 1 to 3 inclusively, and I want them to be evenly spaced. Okay, so I get these numbers increasing by the same increment every time from 1 to 3. So for example, if you're implementing finite difference methods to solve some differential equation, for example, this is quite often you want something like this. Okay. So just note that the first and last numbers, by default, that last number that you put is included. Okay. By default, the last number is there when you use this construction linspace. Okay. Now, I didn't specify how big it was. By default, it said, okay, I'll give you 50 numbers. Here are 50 numbers that go from, here's an array consisting of 50 numbers that go from 1 to 3 with equal spacing between them. Okay. Now you say, well, okay, actually, I didn't want an array that was that big, right? You're just starting to write your code. You only want to use it with small arrays first so that you can see everything that's going on, and then later you'll do it on big numbers with big arrays. But for now, I want only an array with 10 numbers. So you can specify that. So there's a parameter called num, and you can specify it by saying num equals 10. So now if I say np.numSpace 1 to 3, and by default num will be, if you don't write num, but you just write 10 as the third argument to linspace, it understands that you mean num. I think it's actually better to write num equals 10. Let's be clear about what everything means. Okay, write it in, I think. But anyways, all right. So linspace 1 to 3, comma 10 means an array of length 10. So this is a numpy array with the numbers going from 1 to 3 with equal spacing between the numbers, and there are 10 of them. That's the length of the array. Okay, and if you wanted to write in the names of all the parameters, you would say there's a parameter called start. This is 1, stop, which is 3. So start at 1, stop at 3, give me 10 numbers. And linspace means it's an array with all of the numbers equally spaced between them. Okay, is that all right so far? Okay, there are other parameters, and like I said, I think maybe it makes your code clearer if you write the names of the parameters instead of depending upon defaults. Okay. Okay. Now, what if we didn't want the last number? So let's say that this array of numbers represents something like 1 over 1 minus x, right? And I want to see what 1 over 1 minus x looks like on the interval from 0 to 1, but I can't include 1, right? So if I wanted to, so now I want an array of numbers that I'm going to feed into this function 1 over 1 minus x, starting from 0 and going up close to 1, but not actually getting to 1. Otherwise, the function, when I feed it into the function, it'll give me something undefined. Okay, so I don't want the endpoint. Okay, well, this linspace has a default parameter called endpoint, and it sets endpoint equal to false by default. Oh, sorry, it sets endpoint equal to true by default. So if you want endpoint to be equal to false, you're going to have to write that in. Okay. Right. So now if I write something like, I'm going to call this array is going to be called step. It's going to be created by linspace. It's going to run from 1 to 3. I want 10 numbers. And sorry, okay, sorry. And okay, just a sec. Just a sec. Let me fix this. I hope. Just run it right now. Okay, so sorry. All right, so if I said start at 1, end at 3, stop at 3, 10 numbers, and I don't want you to go as far as 3, so I set endpoint equal to false. So now it gives me these equally spaced numbers going from 1 to 3, but they're not stopping at 3. Okay. All right.
Professor?
Yeah.
When we use endpoint is equals to false, right? So it's giving us 10 values.
Yeah.
If we didn't use endpoint equals to false, would it consider 3 to be the 10th value, or would it just give us 11 values?
Okay, well, let's see. Let's say I set it equal to true.
Okay, so
Yeah.
it's taking 3 to be the last value.
Yeah. Okay, so it's going to do that by default. So if you don't want to do it, you actually have to go in and make sure that it doesn't do it. And this is what you get. You won't go as far as 3. Okay. Now, again, like I said, this would be typical if you're writing a finite difference code for trying to solve an ordinary differential equation. So you'd say, I want to go, the interval over which the function is to be solved is, yeah, there's a question.
Yes, sir. So basically, I wanted to say, when does it know where to stop? So if it is going from 1 to 3, should it stop at 2.9, 2.999, or where should it stop?
That's going to depend upon you're going to tell it how many numbers it's going to have, right? And it'll stop one short of that.
Okay.
Yeah. All right. So supposing now I've said it's going to go from 1 to 3, and it's going to have 137 elements, right? And they're going to be equally spaced. And I want to know what the spacing is. Okay. So I can ask it, I want you to return that spacing. That spacing is called a step. So there's a parameter, ret step, meaning return the step. That's usually set equal to false. But if you want to know what it is, then you set ret step equals true. It means it will tell you the step size, the spacing between the values in this array. Okay? So now Linspace is going to return 2 things. It's going to return that array, which is set up according to those parameters, and it's going to return the step size. So now I say X, which is the array, and the step size. These are the 2 things that are being returned by Linspace in this case. So what do I want to call them? Well, I want to call the array X, and I'm going to call the step size step. The spacing between the elements, I'm going to call it step. That's equal to np.linspace. Start from 1 and stop at 3, 10 elements, and please tell me what the spacing or the difference between successive elements is. So now it prints the array, right? 10 numbers between 1 and 3 equally spaced, and it gives me the step size between the 2 of them, and that was 0.2 repeating. Any questions about that?
Sir,
Yes?
I was thinking, what if I want to do a Linspace and I do not want to include the left endpoint?
Oh, I'm not sure. I haven't considered that. You should check the documentation. If maybe there's a start point equals false also.
Professor, what
Oh,
are
actually, let's
tell-
just try that. Maybe there is, right? Yeah, no, it doesn't like that. Okay. All right, so yeah. Okay.
Professor, when
and
we write X comma step, what do we mean there?
where?
In index 45, when we're saying X comma step is equals to.
Oh, okay. So let's say I don't write ret step equals true, right? If I just write linspace of 1, 3, 10, what that means is return an array of numbers from 1 to 3, 10 of them equally spaced. If I say ret step equals true, what that means is in addition to the array that you are returning, please also return this value, which is the difference between successive elements. Okay. So
Understood.
now,
And it's saving value in step.
yeah. So now Linspace is returning 2 things. So on the other side of the equal sign, I have to have something to hold those 2 things that it's returning.
Got it. Thank you.
Okay. All right. Any other questions? Okay. I'm going to then I'm going to stop the share, I hope. Yeah, sorry, this is. Okay, so hopefully I've stopped the share. And I will, in a moment, hopefully I will share the next next notebook with you. Okay, can you should be saying something that says introduction to SciPy. Are people seeing that?
Yes, sir.
Okay, so we talked about NumPy. Now I'm going to talk about SciPy, which makes use of NumPy. And later on, we'll talk about, probably there isn't time today, matplotlib and SymPy are also useful to us. Okay. So let's say that I wanted to, we wrote our own bisection and fixed point and Newton's methods before, but because these are standard algorithms, people do them anyways. People have written up routines for doing these and put them into this module called SciPy, and a part of SciPy that's called Optimize. Okay, so I'll show you an example of using the bisection method in SciPy.optimize. Okay, so let's say that my problem is to find a root of cos squared x minus x plus 6. I do a plot. I see that there's a root somewhere between 6 and 7. Okay, and now I want to use SciPy's bisection method to find the root. Okay, so what I'm going to do is I'm going to import SciPy.optimize as optimize, and I'm going to import NumPy as MP. And the reason is that I need a function. I need this cosine function, and there's a cosine function which lives inside of NumPy, so I'm going to use that. Okay, so np.cos. So if I want access to those, I have to import the modules which contain them. Okay, so SciPy.optimize, I'm importing that as optimize because it has a method which is called bisect. Okay, and a numerical algorithm called bisect which implements the bisection algorithm. And I'm going to import NumPy as MP because NumPy contains a cos function, which I can call. Okay. Now, what function do we want to use? We need to define this. What function are we trying? We're trying to find a root of cos squared x minus x plus 6. We want to find a root of this function between 6 and 7. So we need to define this function, cos squared x minus x plus 6. So define a function, func of x. And what are you returning? Well, cos squared x minus x plus 6. Where's this cosine function live in? It lived in the module NumPy, which I've shortened to NP. So NP times cos of x, I'm going to square that, subtract x plus 6, and I'm going to return that value when I call this function. Okay? So now, there's the bisect method is the numerical algorithm, which is the numerical method which implements this bisection algorithm, which some nice person has already written for me, which lives in SciPy.optimize. Okay, so now I'm just going to say result equals, call the bisection algorithm. This is bisect. It lives inside of optimize. Well, SciPy.optimize, which I've imported as optimize. What's the function whose root we're looking for? Well, I define that as func. What are the endpoints of the intervals? Those were 6 and 7. I want you to look on the interval from 6 to 7 for the root. And now you go and do it. I've forgotten how it works, so I'm not going to write the code. You just go and do it. It goes and does it, and it returns the result. Okay, so we don't have to write it ourselves. And there would be other parameters that you could feed into bisect, right? But look at the you might be able to change the tolerance or the number of iterations or something like that, right? But this is the most basic way of calling bisect. Is that okay? Okay.
Yep.
Newton's method. Remember Newton's method, you had to do this xi plus 1 equals xi minus f of xy over f prime of xy. You're looking for when f is going to be, f of x is going to be equal to 0. So let's say the problem is x cubed plus x plus 1. We want to know when that's equal to 0 approximately for what value of x. Okay, what methods do I use? Newton's method requires me to know f of x and f prime of x. So I define f of x as x cubed plus x plus 1. And I define fp is another function, which is the derivative of x. That's 3x squared plus 1. Okay. So this is an iterative method. So you always need to know a first iteration x of 0. So let's say x of 0 is equal to 0. Now we can call Newton's method. Okay. Newton's method lives in SciPy.op. Okay, there is a Newton's method. There's probably other Newton's method in other modules, but the module I want to use is SciPy.optimize, which I called optimize. So call the Newton's method, which lives in optimize, using these parameters, the function, the initial guess, and the function which defines the derivative, and print the result. So it says that at minus 0.6823, I think that f of the result is very, very close to 0. And in fact, f of the result is some very small number. Okay. So that's how you can call a Newton's method if you need it. Okay. And SciPy.optimize also has a fixed point method called fixed lower line point. Okay. So you remember those methods are written in the form x equals g of x. All right. So let's say we wanted a solution of x over 2 minus sine of x is equal to 0. We write that as x is equal to twice sine of x. Okay. So NumPy has a sine function, so we're going to be calling np.sine. And the function to be called is this thing which is on the right here, twice sine of x. So define a function f, return 2 times np dot sine of x. Okay, let's say the initial guess was x0 equals 1.9. Again, how do you call that? Well, fixed point lives inside of SciPy.optimize, which I've abbreviated as optimize. So the result is optimize dot fixed point, called fixed point, using the function f and using the initial value x naught, print the result and print f of the result, which should be the same. And in fact, it is. Okay. Once again, the documentation should have a lot more about different parameters that you could use. Some of those parameters might be things like the maximum number of iterations or the tolerance, things like that. Okay. So I had hoped to get to plotting, but I think that's enough for today. Okay. Are there any questions?
Professor, would we be getting assignments or problem sets, because we've covered
Yeah,
a lot of stuff?
Riaz sent me some problem sets and I tried to upload them. I've had trouble uploading to the LMS. It's apparently some sort of a storage issue. So I am looking for alternatives to the SMS. Probably I'll put everything on the OneDrive. So the next day or two, I'll get the problem sets to you. Okay.
Thank you.
Right. Any other questions?
Can you explain the line result and print result in Newton method?
In Newton method. Okay. Okay. So so Newton's method runs and it tries to give you your approximate root. So the result will be the approximate root that's given by Newton's method. And so the approximate root is this minus 0.68232. Okay. Now, what's supposed to be happening at this approximate root? F of that approximate root should be approximately 0. So I've asked it, what is F of that result? It should be a number close to 0. And it's, on the order of, 10 to the minus 16. Which is, okay, we'll say that that's good enough.
Okay, thank you very much.
Okay, right. Any other questions? Okay, if we're done, then I will see you on Friday. Okay.